Every single year, humanity discards over 1 billion tires. Left in landfills, they are highly flammable, toxic, ticking time bombs. But inside a high-tech recycling megafactory, these indestructible rubber monsters are violently torn apart to build the indestructible highways of the future. We are going inside the fuel, high-speed process to see how millions of discarded tires are magnetically separated, pulverized into microscopic crumb rubber, and chemically blended into liquid asphalt. This isn't just recycling, it's a massive mechanical resurrection that creates roads that last twice as long, reduce traffic noise, and survive the harshest weather on Earth. Let's look at how it's built. Before we talk about solutions, let's understand the scale of this crisis. Every year, 2.5 billion tires are produced worldwide, not millions, billions. Furthermore, a tire does not simply vanish when it reaches the end of its useful life. Rubber is not biodegradable, not for 10 years, not in 100. A tire dumped in a landfill has the potential to outlive whole civilizations. Tires that accumulate in open landfills collect rainwater, which makes it ideal for insects and disease to grow. They emit a poisonous mixture of sulfur dioxide, carbon monoxide, and toxins into the environment when they catch fire, and tire fires are infamously difficult to put out. The issue of tire waste was ignored for many years. Ignorable, yet manageable. That is rapidly changing. The global tire recycling market was valued at over $9 billion in 2024 and is projected to reach nearly $18 billion by 2033. Governments, engineers, and entrepreneurs are all betting big on one idea. Your old tires can build the roads of tomorrow. The recycling process, step by step. So how exactly does a worn-out tire become a road? It's a process that's equal parts engineering and alchemy. Let's walk through it. Step 1. Collection and sorting. Recycling facilities receive tires that are nearing the end of their useful lives from garages, dealerships, collecting drives, and municipal initiatives. They are arranged according to size: off-road giants, truck tires, and passenger tires. Separation is important since the rubber composition varies by size. Step 2. Shredding. The tires are fed into enormous industrial shredders. Imagine something that could quickly tear a steel-belted tire into fist-sized pieces. These devices process hundreds of tires every hour while running non-stop. The outcome? Rubber chunks that are roughly 2 to 3 inches wide and rough and jagged. Step 3. Steel separation. Each tire is reinforced with a steel belt. The steel wires are extracted from the rubber shreds by strong electromagnets. The process is nearly completely waste-free because this steel is subsequently sold independently, frequently back into the steel industry. Step 4. Granulation. The rubber chips move into granulators, essentially high-speed grinding miles that reduce the rubber down to fine particles. These particles are what the industry calls crumb rubber. Depending on the intended use, crumb rubber can be anywhere from the size of a pea down to fine powder. Step 5. Fiber removal. Tires also contain nylon and polyester fibers. After granulation, a combination of vibratory screens and air classifiers blow away these light fiber fragments, leaving behind clean, pure crumb rubber. And here's where it gets interesting. That crumb rubber, once a discarded, worthless tire, is now a premium industrial input. It can go into playground surfaces, athletic tracks, shoe soles, and industrial flooring. But its biggest and most impactful destination? Crumb rubber meets asphalt. The transformation from tire to road happens at an asphalt blending plant, and it comes in 2 primary forms. The first is referred to as the wet procedure. At a temperature of about 180 degrees Celsius, crumb rubber is mixed straight into liquid asphalt binder. A thicker, more elastic asphalt mixture is produced when the rubber swells and integrates with the binder after partially dissolving. Although manufacturing necessitates specialized equipment and precise temperature control, this is the premium process that yields a superior product. The dry process is the term for the second. Here, some of the stone aggregate in the mixture is replaced with crumb rubber. It is becoming more and more common for road resurfacing projects since it is easier to use and requires less modification to current equipment. Rubberized asphalt, a paving substance that resembles regular asphalt but reacts drastically differently under pressure, temperature, and traffic load, is what comes out of the plant in any case. More than 8,000 used tires may be used to resurface 1 mile of a 4-lane highway using rubberized asphalt. That is 8,000 tires that are permanently locked into infrastructure, and WIL continue to be helpful for decades. Why rubberized roads are better. For anyone working in engineering, building, or urban planning, this is where it becomes quite appealing from a professional standpoint. Rubberized asphalt is more than simply a positive thing for the environment. It's an improvement in performance, resilience. Heavy traffic and temperature fluctuations cause conventional asphalt to crack. Because rubberized asphalt is elastic, it flexes rather than breaks. According to field research, it can outlive conventional mixes by up to 50%. Without maintenance, roads that typically require resurfacing in 8 to 10 years can last 14 to 18 years. Noise reduction. Most folks are surprised by this one. Instead of reflecting sound, the rubber produces a flexible, porous surface that absorbs it. Noise reductions of 3 to 4 decibels were measured in Arizona neighborhoods close to rubberized highways. Inhabitants can really feel and hear the difference. Cost efficiency. A 2-inch rubberized overlay can save as much as $22,000 per lane mile compared to a 4-inch conventional overlay. Less material, less labor, less maintenance. Over the life cycle of a road, the numbers are compelling. Safety. The textured surface improves skid resistance, especially in wet conditions. Better grip at highway speeds isn't a minor detail, it's measurable in accident reduction. In 2024, the U.S. government made $800 million in grants available specifically to incentivize low-carbon pavement technologies, rubber asphalt being one of the key targets. States like California, Arizona, Texas, Florida, and Georgia are already mandating or actively piloting rubberized asphalt on major projects. And in March 2024, Janan opened a Houston facility processing 100,000 tons of tires annually, producing high-purity crumb rubber specifically for infrastructure. This isn't a prototype, it's scaling. There's a concept in engineering called a circular economy. The idea is simple. Nothing is truly wasted. Everything is a resource waiting for the right process. Old tires are the perfect example. Something that was landfilling itself into an environmental crisis has been re-engineered into a high-performance infrastructure material. Over 1,000 miles of roads are being built using rubberized asphalt in the United States every single year, and that number is climbing. The next time you're on a highway, smooth, quiet, holding its lane in the rain, there's a chance you're driving on someone's old tires. Not despite that fact, because of it. If you found this breakdown useful, hit subscribe. We cover complex industrial processes like this one every week, breaking them down for the professionals building the systems that keep the world running.